Hello everyone and welcome back to Introduction to Number Theory. In the previous video, we learned about Minkowski's lemma or Minkowski's theorem. Now, it doesn't matter you say lemma or theorem, Minkowski's statement. And in this video, I would like to show you an interesting application of this theorem on a problem which is a very famous, which has a very famous situation. Let's look at the picture. I believe that many of you see not some blue points in orange circles, but trees on a square lattice. Suppose that we're in a forest, and trees in this forest form a standard square lattice, and all trees are just the same. They're perfectly round with the same radius r. So r is the radius of all of these trees. And instead of one of the trees, there is us. So we're standing in the forest, and one of the lattice points is taken by us. So suppose that we are this point itself. And now we're looking at some direction, any direction whatsoever, just from this point, and our sight is just a ray beginning from this point at some direction. We see that this ray reached a tree. As you may know from, as you may remember from another part of this course, which concerns Kroneker's theorem, we know that any ray whatsoever will sooner or later come up with a tree, intersect with a tree. So there will be no infinite rays from this point. But an interesting question is, okay, but can we mark a distance such that beyond this distance nothing is seen from this point? I mean that can we describe a circle, determine a radius of such a circle, so that the trees inside this circle are hit by, so that all the rays from this point hit at least one tree inside such a circle? What should be the radius of such a circle? It appears that such a radius exists and such a circle exists. What's more, we know that if we take arbitrary r greater than 1 over r small, 1 over r, then nothing beyond this distance will be seen from this point. Any ray from this point will hit at least one tree inside this, well, comparatively large circle. And to prove this, we will need Minkowski's theorem. Namely, consider arbitrary ray. Well, maybe not this one. This is a bad example because on the picture we see that this ray hits no trees inside the circle with radius r. But let's forget for a minute that the first tree is over here. Consider it as an arbitrary ray from this point, and thicken it, make it thick by r small this side and r small this side. So we have not just a ray, but something like a rectangle. All the way here. And the area of such a rectangle will be equal to r multiplied by r small, but the thickness of the rectangle, its shorter side, is not equal not to r but to 2 times r. So r multiplied by 2, which is greater than 2. So we know that the area of this rectangle, I mean this rectangle, is greater than 2. Now a small but convincing trick. Let's just consider the symmetric image of this rectangle according to this point. So suppose that we simply shift it over here. It will look something like this, but we will not need this part here. I will draw it only to show you what I mean. So its length should be the same. And this big figure is obviously centrally symmetric, obviously convex, it's a rectangle, and its area is greater than 4, because area of its half is greater than 2. So Minkowski's theorem can be applied to this big rectangle. And we know that in such case there is a node of the lattice inside the rectangle. For instance, this one here looks like it's inside the rectangle. But this means, since the thickness of 1/2 of the rectangle is equal to the thickness of a tree, well, by thickness I mean the radius of a tree, from this it will follow that the tree with center in the point that occurred inside the rectangle, the tree with center in this point will intersect with the ray, and this is the tree that the ray will meet before leaving the big circle, before going to a distance greater than r. So any such r is a distance such that nothing is visible from this point, nothing outside this distance, nothing more far than this distance is visible from this point. So now we know the exact, almost exact answer. Where is this boundary?